Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So in the last lecture we were looking at the negative index materials and more generally metamaterials, and we talked about how to engineer the electric and magnetic responses, and we saw that over the decade, starting from 2001 to 2009 and 10, there was a lot of activity in the metamaterial community trying to fabricate these materials with unique properties. But towards the end of the decade, towards around 2009-10, people started realizing that if you really have to make three-dimensional metamaterials, it is quite challenging. The reason being that you have we saw that we have to make multiple layer depositions in the case of things like hyperlens or metal dielectric composites. So if you want to deposit 15-20 layers, it's extremely time-consuming, and also the roughness of the layers starts becoming an issue. So that was one of the fabrication challenges that people faced. And in addition, the sizes of the structures are also very small, that the nano fabrication techniques were not able to fabricate structures much smaller than, we were not able to fabricate structures with sufficiently high quality. So even though we were able to demonstrate things like negative index, the figure of merit, which we can define it as the real part of index to the imaginary part of index, that was not sufficiently high, and it is in fact a challenge that is still open. But around 2011, another important direction came into research focus. So that was primarily driven by a paper from Federico Capasso's group at Harvard, and this seemed like a big breakthrough. And the next 10 years, that is starting from 2011 till even recently, we are looking at what we call as metasurfaces. Okay, so we introduce metamaterials, and metasurfaces are essentially two-dimensional analogs. Ideally, if you take a piece of glass, it's a three-dimensional material with a regular lattice of let's say atoms, but that becomes very, very challenging to do in terms of metamaterial. If meta atoms, we can't stack them in 3 dimensions very easily. So people started saying, okay, what can we do with just a 2-dimensional arrangement of these meta atoms? Okay, that whole domain is now called as metasurfaces, and we will try to understand how what are the properties of these metasurfaces. To start with, I want to talk about how do we steer a beam. For example, I have a plane wave which is incident on a surface or an interface, and I want to bend it at a particular angle this way. How can I realize that? If we were looking at the traditional optics, we'll have to go back to the fundamental principles. One of the fundamental principles of wave propagation is Huygens principle, which says that every wavefront introduces secondary wavefronts, and then those secondary wavefronts propagate in a spherical fashion. Like for example, this beam will introduce a secondary wavefront here, and that will start propagating in wavefronts like this, and another point will again contribute another secondary source. All of these wavefronts will propagate, and eventually you will have an overlapping. The overlap of the phase fronts is what defines the direction of the beam, and that is how we get the beams propagating at an angle. But how do we achieve that? If we look at the traditional way of doing the standard, centuries old bulk optic way, we'll have to create a wedge. A wedge could be something like this. I'll create a structure which is a triangular piece like this. And let's say if I shine light on this, what happens is if I shine light in this edge here, there is a thick piece of glass. So the phase fronts are slowed down, and we saw how the phase front propagate in glass, right? So the phase fronts here are slowed down. I should tilt it a little bit. The reason they are slowed down is because there is a thicker piece of glass, whereas in the other side, the phase fronts move faster. Okay, phase front moves faster. So when such a scenario happens, then we can see that the overall envelope of these Huygens wavefronts will actually be tilted in this fashion, and then the beam bends. So that is a fundamental way of thinking about it, and that's what a prism does also, essentially. Now, we cannot in practice create a continuous wedge, or this I can call it as a phase gradient as well. In practice, I cannot create a continuously changing phase gradient, but we know from our basic understanding of how the waves propagate, we can wrap phase at 2 pi. For example, if I have continuous gradient like this, let's say a gradient which is 0 to, let's say, even 10 pi, or let me say 8 pi here. If I have such a phase gradient, I can simply wrap at 2 pi, and then I can create a triangular phase, triangular profile like this. I go from 0 to 2 pi, come back to 0, and then to 2 pi, and so on. If I do this, this will have the same effect as having a phase profile which is going from 0 to 8 pi. So these are equivalent optically. Equivalent, right? These are equivalent optically. Now, how can I create a phase front which is like a triangular fashion? In even late 80s and 90s also, people have looked at what are known as blazed gratings, wherein they take a piece of silicon dioxide and they try to form this wedge, or the triangular shape of triangular profile. And with that, they were able to very nicely bend beams at different angles, and this whole thing was called as blazed grating. So this is well known. Now, in the year 2011, what Federico Capasso's group did was they tried to come up with an alternative way of generating these phase gradients, and for that they used plasmonic antennas. Okay, we have already studied plasmonic antennas, the basic, the sphere, and then the we looked at even split ring resonator is one form of an antenna, and then even we looked at that triangle, the bow tie shaped antennas, and so on. So now let us look at, just for a moment, to understand the idea. Let's consider a situation where I have a simple rod. Okay, this is a PEC rod. Now PEC means perfect electric conductor. If I have such a metallic rod like this of some dimension, and I fix my wavelength and scan the length of the rod, if I do that, I'll see that this antenna exhibits a resonance, and in this case the resonance is exhibited around let's say 0.45 or 0.48 in the lambda L by lambda units. There's a resonance, and associated with the resonance we see a phase change. So just like any resonance you will come across in LC resonators and so on, you will have a phase change across the resonance, and the phase varies from about pi, and this is units of pi, so from pi to about 0.2 pi or so. So across the resonance you see this phase variation. And now suppose I'm able to pick up the sizes in such a way that I'll cross, like for example, I'll pick up here in this situation, I'll pick up 4 points. Let's say this, and this. Let's say I picked up these 4 points. That means I'm picking up that particular size. L by lambda I'm picking up. So this is a small size and then big size. So if I arrange these antennas, let's say one small antenna, bigger antenna, more bigger, and more bigger, then I'm introducing different phases across that. So when a light wave, so essentially my triangular phase front, that is ideal phase front for the blazed grating, I can sample it with plasmonic antennas. Okay, so that is what I'm showing here. So let's say you're able to sample phase gradient with plasmonic nano antennas. Okay, so this is the idea that Professor Capasso's group came up with. You might say, so what? So I mean, okay, yeah, you're able to sample, but it turns out that the implications are quite significant. It's as fundamental as revisiting Snell's law. The example here is, we have seen Snell's law already. Let's say you are having an interface between two materials, N1 and N2, and then there is a light incident, and then it's exiting from medium N2. We know what is Snell's law. This is standard thing we have seen already. Now, suppose, and we also understood what is the physical basis for this, for deriving the Snell's law. We said that it's essentially conservation of tangential component of the momentum. We derived Snell's law already. Now, in addition to this classic case, what if there's a phase gradient at the interface? Like what we have shown in the previous slide. I'll create a phase gradient, and there is some, actually I should say gradient of phase divided by a gradient, right? So d phi by dx. This is d phi by dx. So I'm introducing these antennas which will create this phase, and then there is a periodicity associated with this d phi by dx. So what will happen if I do that? Well, this is like a momentum. There is a discontinuity in the phase at the interface. So we can write the same momentum conservation relation. So we have the momentum in the first medium, in the second medium, and then at the interface, the discontinuity. It's essentially the boundary condition. Just like when you have two electric fields in two media, E2 minus E1, that should be equal to sigma by epsilon, right? Similarly, you should have the phase changes here should be equal to the phase gradient, and that is essentially gradient of phi. Why would I put in k naught here? Does this make sense? On the left side, refractive index doesn't have any sign. This is having no, not sign. It doesn't have any units. Dimensionless. On the right side also it should be dimensionless. So we said this gradient of phi is d phi by dx. So I need to have the appropriate units to make it unitless. So I should have lambda by 2 pi. So that's why I'm putting a k naught here. Okay. So this is essentially my generalized Snell's law. Okay. And it's a very powerful tool that, for example, if I have a large phase gradient. So if I have a traditional material, I should have, for example, if I am having incidence in this direction, if it was a regular material, I should have bending in this direction. So this is theta 1, this is theta transmit, and this is my, refraction, regular refraction, right? It should happen. But because I'm introducing a phase gradient, I can even force my ray to bend in the negative sense. In a way, I can go on the same side and same side of the normal. That means, it's not truly negative, but I can negative in quotes, negative refraction. Okay, negative refraction. I mean, the convention is that, okay, it's not negative index. It should be, it's only negative refraction. It's not negative index. I can have it in the opposite direction. So it gives us enormous flexibility. That's what we were after, right? When we talked about the negative index media, we said that it can bend in the negative sense, and that gives us more flexibility that is not present in nature. Now, after 10 years of research, people realize that you can even do it with a simple array of planar, antennas. Okay, that's why it caught a lot of attention, and quickly people started, running after this. A lot of research groups parallelly started working on this, and the whole area of metasurfaces that we have been talking about for last 10 years is essentially that. Okay, so how do we do that? Well, it depends on the k naught is fixed, so gradient of phase. So d phi by dx. So how abruptly I'm able to change. For example, let's say I give you a scenario wherein let me go back to the previous case here. So let's say this distance was let's say 1 micron. Okay, I'm able to change 0 to 2 pi in 1 micron. So my phase gradient is 2 pi by 1 micron. So that's whatever, you get in the units of per meter, right? You get that. Now, instead of that, I'm able to change it in only 0.5 microns. So if I double my phase gradient, then automatically my angle will change, right? So if I want to bend it, this was the normal case when phase gradient is 0, it goes in this blue. Now, as I increase this, I can make it go in the other side. If I have a stronger phase gradient, I'll go further down. So the phase gradient determines how much bending happens. In addition to the wave vector in the incident and the transmitted medium, we also have to have a strong phase gradient. Does that answer or? Okay. Yeah.
Then you can have any angle of any exit angle.
Okay. So the question is, so basically you have any angle of refraction. Well, the problem physically will turn out to be, how much is the gradient you can generate physically, and I'll talk about that just in a moment. Okay, in the next slide I'll talk about it. Okay, so the idea is we are trying to put antennas, right? If you have a certain size of antennas, there's only finite number of them you can put. You can't really put, these are not infinitesimal antennas. These are not point dipoles. These are having some physical extent. I'll show you some examples, of the physical extent. So once you have two antennas, I can't merge them. I can't overlap them. So that spacing between the antennas is eventually what will determine my bending angle. That's the physical limit that comes in. Okay. So yeah, so this was, this seemed very exciting. Of course, people have known about it, but this is how, you see so many times science progresses. So we know something, and then we take it for granted, and then someday we discover and some other perspective to the same thing. So that way this was interesting. All right. So how do we generate this? Well, I showed already this kind of, if you have a simple rod antenna, you will see that there is this amplitude and the phase variation. But if you notice carefully, this rod antennas have basically limitation. Rod antennas can provide phase shift of about pi, not 2 pi. That's a problem, because we really, if you want to control from 0 to 2 pi, we need the entire gamut, right? So how do we achieve that? It turns Kapas's group again proposed the antenna, they introduce these V antennas, which are essentially, instead of a rod antenna, I'll bend it, okay? And the length of the antenna and the angle with which it bends, So basically, let's say if I have my V shape like this, this is basically a rod. It's a kind of, you can think of it like a bent rod. So this is my, let's say, the height, or the length h. I think they call it h, so I'll keep it the same convention. And this is my delta, which is the angle. Okay. So the angle with which you're bending and the h is what determines. This is again, if you take a, if I take a rod antenna of size, if I take a rod antenna like this and say, let me say this length is 2h. So there will be multiple modes that are excited. The fundamental mode in this structure would be the half wave dipole, right? So the plus and the minus. So in this case, this resonance will occur at lambda effective equal to, let's say, 2h. This is my fundamental mode. But in addition, you can also have a higher order mode. So you can have a situation wherein you have the rod like this, and then you can have a situation where this plus, minus, plus. Okay. And this will be again 2h. So if I have a higher order mode like this, this mode will be excited roughly when lambda effective equal to h, because half of it, right? It's essentially. And you'll also notice the way the fields are. In this case, the field pattern would be, or rather the electric field will be like this positive. Here it is this and this. So there are two opposing fields. Now when you bend it, Kapas's group said that, okay, they can have two different modes, and they call them as symmetric and the anti-symmetric mode. So that is what is shown here in blue is a symmetric mode. So essentially what you have is, you take an antenna like this of some V shape, and then you have an incidence in this direction. So you can resolve the incident electric field into two orthogonal components, the symmetric electric field and the anti-symmetric electric field. So when you have a symmetric electric field, you see that the dipole, essentially the antenna behaves essentially as this bent antenna with two arms, and electric field in both arms here represented in blue are in the same direction. That's why it's called as symmetric mode. And we already saw that the symmetric mode, it will be like this, right? This is a symmetric mode here, because if I bend this particular antenna in the bottom here, if I bend it, I'll see that both the arms, you have the currents in the same direction and you have the hotspots. So this is a symmetric mode. And you can also have one more case wherein if your electric field is perpendicular to this, anti-symmetric component of the electric field, it can excite this anti-symmetric mode wherein you have the current going from this to this, right? The entire thing. So for an anti-symmetric mode, your resonance is going to be roughly 2h, right? Lambda effective is going to be 2h. Whereas for the symmetric, this is lambda effective. If I say this is going to be 2h, and this is lambda effective is going to be h, only in the length, right? So this is my, if I talk in terms of plus and minus, so this will be my plus, minus here. Whereas in this case, there is a plus and a minus, the entire length of the antenna. So you have these two modes that are supported. And the beautiful part is, if you have two of these modes, the entire, the phase change that you can achieve with these two resonances, which are kind of, in the same antenna structure, you can get the entire 2 pi phase change. And that is what is shown in the bottom picture here, wherein you are essentially, this analytical calculations of how this antenna behaves for various angles, the delta angle between the wedges, the two parts of the V, and then the height is essentially, h is essentially not the length of the antenna. So what you see is, for various shapes, you can get essentially some amplitudes, okay? And the interesting part is the phase is on the right side here. You see that the phase is going from, in this case, I think this is minus 3 pi by 2, 3 pi by 4. This is pi by 2, right? So this is pi by 2. So this is minus pi by 2, minus pi by 4, 0, pi by 4, and pi by 2, and so on. So you're seeing that there's a wide range of phase much wider range of phase shift that can be introduced. And so I didn't mention about the amplitude part. It's not enough if you have antennas with different phases. We also have to have them at sufficiently same amplitude so that we don't distort the beam. If let's say you're able to introduce a phase, but then the amplitude is different, then it won't work. So that's why if you notice here, from this entire parameter space, they picked up 4 different structures. One is of this, this shape, 180 degrees. So basically a linear antenna, a rod antenna. And then there is different angles, smaller angles. So you essentially have a V shape. And this entirely they picked up these various shapes at particular, basically, so that the amplitude is same. And in this part here, you see the red line this is anti-symmetric mode, the pink line, anti-symmetric. And then the symmetric. So you see that the symmetric mode occurs at a much longer wavelength, 2H. We said symmetric mode, it should be, wait. Yeah, H has to be larger for the symmetric mode to be there. All right. So this is what you have. And then you have this phase variance. Okay, once we get this phase, you had a question? So basically, if you have a symmetric mode, the electric fields are like this. The symmetric in both arms. But then anti-symmetric mode is actually going the entire way. So the question was, if you have an anti-symmetric mode like this, does it mean that it's a circulating current? Or can it have a magnetic dipole? And indeed, you can actually have, if you compute this, you'll also see that there will be some magnetic confinement in this. So you should see some magnetic response. So in a way that is similar to the split ring resonator. You can think of this as, equivalently, I can also say this V antenna in the anti-symmetric mode, if you have a V shape like this, I can think of this as somewhat equivalent, at least. It's not ideal, of course, there are going to be differences, but it would be similar to a structure like this, a split ring like this, where you have a circulating current, and because of that, there is a magnetic field. So definitely, there will be parallels to that. If you look at the magnetic response, you will see that the effective permeability is not going to be 1, but it's going to be something different from 1. How strong and all that, we have to see. The main thing is the gap was important. It's not like a split ring in true sense, because the gap is quite wide. If you have a very small gap, then you have a capacitance associated with it, then it becomes a double negative structure. But in this case, it's not going to be double negative structure, because the capacitance is not going to be that large. So most likely it's not going to be double negative, but it can potentially exhibit negative mu. We'll have to look at exactly, how much is the strength of that and all that. It depends on, the displacement current as well. Is it really how much? Because it's very far apart. Maybe it will not be. We'll have to see. Okay. But definitely it should exhibit some sort of, once you have a circulating thing, we should see some magnetic response. All right. So yeah. That was a very nice question. So basically, yeah, as you see, it's all interlinked, what we studied in the past, and now it's all, related. All right. So what Kapas's group did was, they took these structures. We only saw 4 of them, but essentially you can take the mirror images of that. So essentially you can get an entire 0 to 2 pi phase. So what they did was, they arranged these antennas in a unit cell. Okay. And that's what is shown here. And this is a simulation. So let's say you arrange it in some, this gamma here, in this case, I think 0 gamma by 8 and so on. So essentially they called this entire thing periodicity as gamma. Over a distance gamma, you arrange 8 of these antennas. And so you get 0 to 2 pi change across that. So what will be my phase gradient? In this case, d phi by dx is going to be gamma divided by 2 pi divided by gamma. Yeah, 2 pi divided by gamma. This is my phase gradient, right? So now, if I am able to, the question previously was, how small can these things be? Now, these antennas are some sizes, some h, right? What was a h? Typically about, let's say on an average 1 micron. If I want to put 8 of these devices, roughly I need to have at least 8 microns periodicity. Can I put 8 of these antennas in 4 micron periodicity? Obviously not. Okay. So essentially it is going to be a trade-off between how accurately you sample the phase and what is the physical dimension. For example, if I say, let's say this my structure is like this, right? And this is my 0 to 2 pi phase I want to achieve. 0 to 2 pi. Now, okay, ideally I should just sample it at every point, right? If I sample it on, let's say I'll only put 8 points here, or 5 points, let's say. That may be enough, because as long as you satisfy Shannon's sampling theorem, it should be fine. You should get some response. But if you are very, very close to the continuous gradient, you will get best efficiency. So you're going to sacrifice efficiency. If I, let's say, instead of this, I'll become, I'll say, no, I want to actually have a very strong gradient. Okay. Of course, I'm not able to go, I will not be able to pack, let's say, 8 antennas in the 8 micron space, or, 8 antennas in 1 micron space or 2 micron. So what I'll say is I'll sacrifice my sampling. I'll put only 2 antennas. Then I'll essentially pick this and this 2 antennas to sample this. So I'm going to pay the price in terms of efficiency. If I try to have very large angles, at some point I'll start paying the price in terms of efficiency and I will not be able to do it. Okay. That will be my physical limit. All right. But in this case, anyway, they took 8 antennas to sample the entire, phase of 2 pi, and fabricated samples are shown on the right here. So you see this same scheme, the V antennas over with different these things. And in the Y direction, they simply repeated them. So there is no variation in the Y direction. Only in the X direction, there is this phase gradient. So if I ask you what is d phi by dy, what would it be? 0. There's no phase variation across the Y direction, only in one direction. But in principle, I can even create phase gradient in the Y direction, and then I can have the overall effective phase gradient, and because of that, bending can be in any different directions. So that's the beauty of it. Okay. Okay, yeah, if I put phase gradients in X and Y, then is it polarization sensitive? Well, yeah, there will be some polarization sensitiveness, yes. Yeah, right. So, yeah, but anyway, to demonstrate this, they chose only one gradient, and you see that the results in the bottom. This is angle of incidence, and then this is angle of refraction. So, for a particular angle of incidence, you see a particular angle. So, this is without any phase gradient. So, this particular thing is no phase gradient. The traditional Snell's law. So angle of refraction is going to be dependent. You can calculate sine of that. So the solid line is, I think, the theoretical expression, and with some measurements without phase gradient. I don't know what it means without phase gradient measurements, but yeah. I mean, it's Snell's law, that's it. Yeah. But then the red is anomalous refraction, wherein my refraction can even be negative. So this is my this part. This part is my, let's say if I take this red, blue, this is my negative refraction. So essentially, with a particular angle of incidence, I'm able to bend even in the negative sense. And of course, the red line here is the theoretical expression that we said, right? The generalized Snell's law. That is the red line here, and then the experimentally measured data is here. And you see that there's an excellent match. It turns out that, very rarely that we have this perfect matches, but in this case, there is very nice matching. And even the reflection, angle of reflection also matches. You can even have not just refraction, even in, the traditional law of reflection is what? Any surface. If you have a planar surface, the law of reflection is equal to angle of reflection, right? But now I can break it. I can make it go in a slightly different angle from what we have, okay? So that's what we have, anomalous reflection. Okay, we can even change it slightly depending on the phase gradients. The challenge will be how much and all that. We'll have to, it's not a very difficult thing to compute. We can actually do a phase gradient, sweep the phase gradient and figure out what we want to do. Okay, so this was a very beautiful work that came out of their group in 2011. And quickly enough, people got excited. They started doing it. Okay, this was actually, I forgot to mention that. So these experiments were done, I think, at lambda equal to 8 microns. You see the sizes of antennas are all in microns. So basically it's much deep subwavelength, of course, but it was done in the mid-IR because that's where you can easily fabricate these devices. So quickly somebody else tried to do, let's say visible. And then this again, the exactly same thing. There is not much, but the only thing is this is working at near IR wavelength. The same V antennas work. And then you see there is a perfect, and in the bottom, these are the fabricated sample, and in the bottom you have the measured angle of refraction versus wavelength. The important point here is that this can even be broadband. Now previously we just looked at one particular angle, but since we already know that the plasmonic antennas or plasmonic resonances are broadband, you can actually see that effect at a large range of wavelengths. So, and it actually obeys the law. The actual curve is going to be exactly identical. But you see that already the quality of these antennas, if you compare the previous slide, they're all nice, beautifully shaped. But then the moment you come to near IR, the antenna shapes are quite not so nice. And I mean, I must confess that this is actually fabricated by me, and I think it could even be better. It was not the best of samples, but it's what it is, right? So you can improve these things definitely, but at that point we didn't really spend time on that. But you can do slightly better than this, but still overall you'll be limited by the size of the antennas. All right. So this was interesting, and this is what the group had shown. And now you might say, okay, this all looks good. So what? I mean, why should I care? It looks like basic. What applications do you have for this? Well, there are a lot of applications that people have been thinking about. One of them is, we talked about this two-dimensional variation of phases, right? So in the picture on the left, you see that the antennas were essentially arranged in such a way that you create what is known as a phase vortex. So for example, here you start out with 0, and gradually I change my different sections of this square have different phases. So go from 0 to pi by 4 to pi by 2 and so on. So entire phase of 2 pi, if I change, this is called as a topological charge. I mean, if you have a phase gradient, it has a topological charge of 1, and that essentially creates a vortex. In the sense, if you take a simple plane wave and you focus it, you're going to have a uniform Gaussian profile. But then in this case, when you have such a scenario, the electric field actually will be like a donut, or the intensity will be like a donut. There is a gap in between. That occurs when you have a kind of a the topological charge of 1. That is, if I go in one rotation, there's a phase change of 2 pi. Okay. So, and this sort of a thing is expected in the bottom, and this is what is measured on the top. And a few other properties, when you take this sort of a structure and you make a beam incident on that, and you actually interfere that with a, the outgoing beam. If you interfere with a Gaussian beam, you'll end up getting phase profiles like this. This is what is theoretically expected, and exactly similar thing is what we are seeing. And you can have, if you have slightly at a different angles, if you have these beams interfering, then again you will have different structures that are well studied in the laser community, and you are able to see that. So essentially we are able to generate these phase vortices, or in this intensity, as in this form. You might say, what is the use of this sort of a intensity? Well, it turns out that there was a very interesting idea that got a Nobel Prize, I think in 2014, I believe, or for STED microscopy. 14 was the blue light. I'm not sure. Okay, blue light LED. Blue LED was given a Nobel Prize, I think, in 2014, and also maybe STED. I'm not sure. Okay, can one of you check that? It's just Stephen Hell and then others. Okay, they got a Nobel Prize for what is known as stimulated emission depletion. So they use this sort of a annual, beam with a 0 in the center to actually excite. What about the Nobel Prize? Nobel Prize for blue LED. STED is 2014, and blue LED 2014. So it was shared. Okay, blue LED and STED were, that was a shared Nobel. No. Blue LED was shared between Amano and Negishi, and not Negishi, Nakamura and others. STED should be some other people. So anyway, chemistry was STED. Okay. The same year, the physics Nobel Prize for blue LED, and chemistry Nobel Prize for STED. But the STED idea was that if you have this sort of a beam with an intensity 0 in the center, you can actually image biological samples with much better efficiency than what is given by diffraction limit. So if you have this sort of there's a lot of interesting things. As recently as 8 years back, they got a Nobel Prize for something like this. Okay, so you can take it that these are very interesting ideas. So that's one application. Another application is like what I think we mentioned indirectly. So if you have these two-dimensional variations, you can actually rotate polarizations. So for example, here this is I think work of Professor D.P. Sai in Taiwan. So essentially what they took was structures with different profiles, and you can actually convert an incident beam to, let's say, circular polarization, left circular, right circular, linear, or rotated, and all that. So you can create structures which can actually do a lot of polarization operations. Okay, so if you want to do that in a traditional traditional optics, you'll have to have a you have much more bulkier components, such as the optically birefringent materials like calcite, and then you have to make it incident at a particular axis, and it's going to be bulky for it to accumulate that sort of a phase change, right? So you can do that with just a structure, and also you can also make holograms. So for example, in the structures we have seen definite phases, but in principle nothing prevents me from actually taking an image like this and trying to back calculate what sort of phase shift should be introduced. So in this structure on a gold film, this structures with some pre-calculated phase shifts were introduced, and then the moment you shine light on that, you get a hologram. Okay, so these are some interesting ideas that people have pursued. There are also other ideas like plasmonic structural color. This is a very interesting applications people have done. So we saw initially that if you have these resonances, there are colors, but again those nanoparticle sizes and all are difficult to control. But now you can actually have structures with predefined geometries. For example, here let's say there is a metal on the top, metal disc, and there's an insulator, and then there is again metal, and you can have various geometries, sizes and arrangements. With that, we can actually see that you will get the entire color gamut. So this is, you can create structures and you can make pixels out of this. Let's say if I have a periodicity of 20 microns, I'll get some color. If I have a periodicity of 10 microns, I'll get another color. So I can create pixels with varying structural features, and then eventually I'll get colors. And that's the beautiful, colors images. This is, I think, Lena, and then this is some other painting. I'm not sure what it was. Monet or something they call it, I think. Yeah. Anyway, and then University of Southern Denmark. So you see various interesting colors are being generated just by arrangement of nanostructures. You might say, so what? But if you look at it, if you look at the color detail, the DPI of that, the dots per inch, if you calculate, the DPI of these colors will be, the pixels per inch will even be up to 1 lakh DPI, dots per inch. So you're able to get very, very fine resolution colors. And then we also mentioned this, that these are more insensitive. For example, if you have any dye color, that can get spoiled. But if you have a plasmonic structure, nothing happens to that. It just goes on for ages, centuries together without any degradation, like we saw in the French windows, right? Not French windows, those church windows with plasmonic colors. So effectively, you can have a lot of interesting colors like this, and people have thought about it for various applications. Okay, so in effect, the plasmonic metasurfaces were very interesting, and people have been looking at it. So this is where I want to stop for this lecture, and I'll continue in the next. All right. Yeah. Thank you so much. Then I'll see you there.